This is the MAT from 2016. I'll do just the first 10 multiple choice questions. I'll do the other questions in another video at some point. So we have a sequence here. First term 1, subsequent term is defined by L times the previous term. So this next term is just going to be L times 1, which is L. The term after that is going to be L times the term before, which is L, so that's L squared. Term after that, L times L squared, which is L cubed, and so on. What is the product of the first 15 terms? So the 15th term is going to be L to the power of 14, because this is always 1 less than this. And then we're going to multiply all of these things together. Of course, multiplying by 1 doesn't make a difference, so we can just start here, multiply all those things up. Of course, there's a 1 here, and just using these laws, it's 1 plus 2 plus 3 plus 4 all the way to 14. Now, the only sensible answer here is this one here, so we may as well just underline it right now. Otherwise, you might know the n into n plus 1 over 2 formula for the sum of the first n numbers, integers, starting at 1. You can use that, you get it. Anyway, part B. Irregular hexagon with sides all of equal length. So this is the hexagon in here, this kind of shape here. All equal length, I mean, if this was x, this is x, and this is x, and so on. It's irregular because the angles aren't the same, even though the lengths are. Of course, if the square has a side length 1, that means that we can call this little length here 1 minus x. And we can do the same for this little length here, although I won't write it down. And then we can use Pythagoras to say that this squared plus that same thing squared equals x squared. And I mean, there's just some algebra to do here. It's not particularly bad. Choose your favourite way to solve this. I completed the square, but it doesn't really matter. And then you just got a decision to make here. You've got two answers when you solve this quadratic. Only one of them can be correct. Is it this one or this one? Well, x, looking at it, has to be less than 1, and this is definitely more than 1, so it must be this one here. Good. Question number C. So just completing the square things to get a circle here. So halve a to get a over 2, and then take away the square of it. Do the same for B here. So this is a circle, radius root all of this, centre minus a over 2 minus a b over 2. Now they haven't actually told me whether a or b are positive or not, but it doesn't really matter. Let's just say that the centre is over here somewhere. It's not going to make a difference. There's a circle, radius root this, and now for that circle to contain the origin, the distance from the origin to this point here, again, regardless of whether or not a and b are positive, is this. And of course, now we can see why it doesn't make a difference whether a and b are positive, because you're just going to square them anyway. You just end up with 4 points that are all equidistant from the origin anyway. So okay, you square this, and that's the distance from the centre of the circle to the origin. Now, of course, for the circle to contain the origin, you just need the radius, which is root this, to be bigger than this distance here. As long as that radius is bigger, the origin is contained. If the radius was lesser, the origin would be just outside. So I just need that to be bigger than that. Of course, I can square both sides out because we're dealing with positive numbers here. So the roots are defined to be positive, of course, so we can square this out and we don't have any problem with this inequality here. Of course, all of this cancels and we get C is greater than 0. Good. D, how many solutions does that have for integer n? You can do this entirely algebraically, but I think the quicker way is just to choose n as 1 first and solve that equation. So if you put in n as 1, you get this, factorise out, have solutions that cos of x equals 0 or 1 plus cos of x equals 0. Of course, cos of x equals 0 at pi over 2 and 3 pi over 2. You can draw the cos graph to clarify. You also have this, which is this, and then that solution is at pi. So you have 3 solutions when n is 1. So it's not any of these answers. It could be this one. In fact, it could be C or it could be D here. And to choose which one, we'll just choose n is 2, because this one talks about even and odd. So let's choose an even n now. Put an even n in, you get this formula, factorise out cos squared. Of course, this means cos squared is 0, or this is 0. That has the same solutions as this did, because of course you root 0 just to get root 0 anyway. And then you solve this, but of course this doesn't have any solutions, because you can't square something to make minus 1. So you only have 2 solutions if n is 2, and so the answer by deduction must be D. You can algebraically prove it's D, but just by my 2 examples, this is the only thing that's left that's reasonable, so we'll go with D. Good. E. So first thing you always, or at least I always check when I'm doing which graph is which questions, does it go through the origin? If you plug in 0, do you get 0 out? You do, in this case, as long as you know your exact values for cos. Use the graph in the previous slide to help you. So it does go through 0, 0, so it's not either of these 2 graphs, got it down to these 3. You could do more intelligent things here, I think, but what I decided to do was just sort of vaguely plot it. Just try when x is 1, and there's no scale on any of these graphs, so this is a bit tricky, but if you put in x as 1, you get this, because this is 0, but cos pi is minus 1, so you have minus minus 1, which is 1. So when you go across 1, you go up 1. So that could be this graph. It could be this graph if 1 is all the way over here and 1 is all the way up here, though it's unlikely. And I guess it could be this graph if 1, 1 is like here somewhere. But I think we can deduce using x is 2 which one it is. So just put x as 2 into all of this, and you get 1 again, because this is just 1, this is 0. So you get 1. So it goes 0, 0, 1, 1, 2, 1, which is consistent with this graph, roughly. If we're going to guess that's 1, 1, 2, 1 is definitely not on this graph, so that looks completely wrong. And remember, 1, 1 had to be here, so 2, 1 is over there somewhere, so that's completely wrong as well. So A is the only reasonable sketch that we have, I think, that's consistent. Good. F, kind of an interesting question here. You just need to be very confident with factor theorem. So factor theorem says, for some f of x, if, for example, x minus 1 is a factor, then f of 1 is 0. So you use whatever x value makes this 0, and then the entire function becomes 0. So if x plus 1, then you use minus 1 in here, because x is minus 1 makes that 0, and then the entire function becomes 0. Likewise, if you've got a more complicated thing, you just use x as a half in this case, right? 2 times a half minus 1 is 0, so you can get that to work. Now, if that's a factor, what do you have to set x? Well, if you do further maths, you might know you have to set x as plus or minus I, but we can get around that issue, because all we have to say is that we need x squared to be minus 1. Right? We don't actually need to have any knowledge of what that means, because this function, if you notice, can be written entirely in terms of x squared. And then we can just shove this x squared in there as minus 1, and then we should get 0 out, because that's what factor theorem tells us we need to get when we do that, because it's a factor. So we just put minus 1 into here, and then it's just a case of dealing with this. When you've got two things multiplied both to the same power, you can just take that power out like this. In other words, I've just said this is 2 times minus 2 all to the power n, which is minus 4 all to the power n. And then, of course, if n was even, minus 4 to the n is just 4, and then you get 4 to the n minus 4 to the n. And that cancels. So if n is even, this works. If it's odd, it doesn't, because if it's odd, minus 4 to the n is minus some big number, and then you're minus minus and you add together, so that doesn't work. So n is even will make it work, but n is odd won't. Good. G. Now this is an interesting question for a couple of reasons. X0 is 1, so let's just get our heads around what this is defining. So if n was 1, say, we'll be going up to 0 if n is 1, and essentially this is a very boring case. You just put in k as 0 to get x0, and then you don't go any further. So that just equals x0, which is equal to 1. So x1 is 1 as well. So the sequence goes 1, 1. Now x2, you sum up to 1 here. So you put in k as 0 first, then you put in k as 1 to get x0 plus x1, which is 1 plus 1, which is 2. Then the next term, you go up to 2, so you have x0 plus x1 plus x2, which is 1 plus 1 plus 2, which is 4. And now notice a pattern here, which is when you do the next one, this term here is what you just had. And all of these terms, by definition, add up to that term that you just had, because that's how all of this works. So this is just going to be 4, which is how you got this 4 in the first place, plus 4, because that's this 4, which is 8. And the same thing keeps happening, right? The next one will just be 8, because that's all of the previous terms, plus x4, which you just made out of all the previous terms. So you get 16, then you get 32, and so on. And so therefore the sum of 1 over xk is going to be 1 over 1 plus 1 over 1 is the first term, x0, then plus 1 over 1, then plus 1 over 2, then plus 1 over 4, and so on. And this is interesting because you can finish this question very quickly if you just happen to know a result, which is that the sum of all of these half powers, 1 over 2 to the n, all of those, that sum there is just equal to 1. So this is just 1 plus 1 plus all of this is just 1 forever. And so you get the answer of 3. If you really quickly want to prove that, you can do it pictorially. I might post a video in the description of someone doing this very nicely with some pictures. But otherwise, you can just factorize. You can just say that the sum of this is s. Factorize out half from this to get you this. But of course, this here is just 1 plus s, what you defined as s before, right? Because it goes on forever. And then you distribute out the half, you solve it, and you get s as 1. So all of this sum is definitely just 1. So it's 1 plus 1 plus 1 is 3. So it's a good question. This question is just very mechanical. There's probably cheaper ways of doing it, but I don't know. This is a minus x squared, a there, and then root a and minus root a there. Let's just integrate this to be between root a and minus root a, so that's the area bounded by the x-axis and the curve, so that's fine. Of course, this is an even function, it's symmetrical around the y-axis, so I can double this and integrate between 0 and minus a. So literally just doing this integral and doubling it. That's quite a nice trick. The reason it's nice is because when you put 0 into here, you don't have to do anything. So I just need to put root a into here. Now a times root a is a to the 3 over 2, and root a cubed, that's a to the power half cubed, a to the power 3 over 2. Now this is one lot of this minus a third, which means it makes it 2/3 of a to the 3 over 2, times 2 is 4/3 a to the 3 over 2. 4/3 of that, yeah. So that's the first integral. And now let's do the second integral. It's a quartic curve this time. 1/7 of a, and then the roots are going to be the 4th root of a and minus the 4th root of a. Of course, you can do the same thing. It's an even function, despite the fact that I've drawn it a bit off center there by mistake. But I can just integrate between this and 0 and then double the answer. Again, it's just going to make everything a little bit easier for me. Shove those things in there. So this is a to the power quarter. To the power 5 is a to the power 5 quarters. Don't know why that came in late. That was a mistake anyway. And then you put in this and you get a times a to the power quarter. Add the little powers to get a to the power 5 and 4. 1/5 minus 1 is minus 4/5. Times 2 is minus 8/5 of the thing. And the reason the answer is negative, of course, is because it's below the x-axis. And I just need, I don't care about the negative here. I'm just going to change it to a positive because we're talking about total area, not the actual integral value. And I want this area to be bigger than this area. So I'm just going to set that one bigger than this one. And I'm going to solve this for a. So that's what I'm looking at. Let's do some cross multiplying. You can divide both these things by 4, I believe. You can basically circle this answer at this point because it's the only thing. Oh, in fact, actually, no, that's a 6 and a 5 as well, isn't it? Well, I think I decided to be a heathen for a second and write these as decimals. And now if you divide by a to the power 1.25, you can see this is going to be a to the power 0.25. I'm allowed to do that because a is greater than 0, so I'm not worried about doing anything negative there. And then you can just divide by 5, change that back to a quarter, raise it to the power 4 to get a bigger than this to the power 4, which is e. Good. I is a really tough question, the toughest on the first 10 questions, I think. The only way that I worked out to do it was just drawing a picture, and of course that is. So you say, okay, I'm trying to maximize this. Let's just make it k and talk about maximizing k. But now you've kind of made a straight line out of this, haven't you? You can rearrange it to be this, and this is a circle. It's really a disk. You need to be inside of this circle, radius 1. And you want to be on this line. So we think, okay, well, we're trying to maximize k, remember, because we're trying to maximize this, which is k, I've just decided. K is the y-intercept here. So how do we maximize? Well, it sort of is. It's shifted down by b, but it doesn't matter. Or squashed down by b, I should say. So how do we maximize this y-intercept then to maximize k? Well, you can just bring the line up and up. And you just need some point on the line, some value x, y, to still be inside of this disk that you need to be in. But that means we can just move it up until it's just touching it here, and we can just make it a tangent. And so this is the key point here, right? Because this xy value here is just about within this disk, and will maximize k because we've lifted the line up as far as possible on this y-axis, which means we could, because k is that y-intercept there, we'll get a maximum k value out. So this all looks a bit complicated, and it's not like anything I've really done before, which is nice, because it's nice to do maths that I haven't really done that much before. Let's look at this radius here. It obviously meets this line at 90 degrees, because I've chosen this to be a tangent. It has radius 1, of course, because that's this disk here. This line, though, is as of equation y equals b over ax. Because this line is minus a over b, we need to have a negative reciprocal idea going on, right? So we flip this over, times by minus 1, and we get this. It goes to the origin clearly, so this is this line. But I can find this coordinate now by setting this line equal to this one, and solving. And I think I put these two things together, and then times by ab, divide by this, and then these b's cancel, and you get an x coordinate, which you can then just put into here, really is probably the best thing to do, to get a y coordinate. And if you put this x into here, these a's will cancel, and you'll just be left with a b on the top instead. So this is the coordinate this, which looks disgusting, but I think we're pretty much there now, because again, remember that this distance is 1. So I can actually solve for k by doing this thing squared plus this thing squared equals 1 squared. which again looks terrible, but don't actually expand this out. Generally a good rule of thumb is to leave things unexpanded for as long as possible. This top thing squared is just k squared a squared. Now, of course, these two denominators match, so I can just shove these fractions together to make this, and I can also factorize out the k squared from the top. But of course, that means that this cancels with this, and that's why you didn't want to expand out before, to just leave one of them on the bottom, then multiply out, and then square root, and you get this answer here. Because look, the k is equal to this. K was the letter I chose to be the maximum value, so the max k is this. Really weird and interesting question that I can't imagine most people got. I don't think I'd have got that under time pressure. It took me a while to sit here and work it out. But yeah, anyway, this is a nice question. It reminds me a lot of doing Tamura papers, which I obviously love. So n is an integer bigger than 1. I hope that I haven't broken that rule anywhere, but I don't think I have. So this big capital pi of n is the number of distinct prime factors. So for example, capital pi of 15 is 2 because it's just 3 and 5. Capital pi of 21 is also 2 because it's 3 and 7. Capital pi of 24 is 2 because it's 2 and 3. I was trying to think of a different one, but I got that wrong. Capital pi of 120 is 2, 3 and 5, I guess. So that's 1. So that's 3. And then x of n is the final digit of n. So x of 61 is 1, and x of 73 is 3, and so on. Easy. Which of the following statements is false? If the number of prime factors, remember that's what this means, of n is 1, there are some last digit values that mean n cannot be prime. Now, capital pi of n equal 1 means numbers of the form p to the n, where p is prime. So things like 2, obviously, because that's 2 to the 1, or that n I shouldn't have used as an n, should I? That's not the same as this n. That's frustrating that I've done that, but just think of this as a different n, or like as an m or o, or anything that's just not this n here. But it's numbers of the form p to primes to something, like 2 to the 4, 3 to the 3, 5 to the 7. Things that only have one prime in them. I think you know what I mean. Now, x to the n, if the last digit of n is 6, n is not prime, right? And there's a number 16 that comes to mind. 2 to the power 4 is 16. So 16, capital pi of 16 is 1, because it only has one prime factor. But it ends in a 6, and numbers that end in 6 can't be prime. So this is a true statement, right? In fact, this bit's kind of irrelevant, almost, really. Although it's good to clarify that 16 does work for it. But there are, of course, some last digit values that mean n cannot be prime, 2, 4, 6, 8, and so on. But 6 is a good one to take because it has this 16, which obeys this. So that this statement is definitely true. This one seems a bit more complicated to think about, and it involves a lot of testing, so I thought I'd leave it to last. Basically, it's saying, again, if you're dealing with numbers that only have one prime factor, there are some last digits that mean n must be prime. So what I'd have to do is I'd have to find counterexamples of every last digit from 0 to 9, and show that every single one of them has one that's not prime. But that seems like a lot of work, so I'm hoping to eliminate all the others and then just show this one is false by deduction. So let's go to this one again. So numbers that, again, only have one prime factor. There are values of x of n. There are last digits that are impossible. That one's clearly true. You can't end with a 0. Because to have numbers end in a 0, you must have a 2 and a 5 in them. Like, they must have the primes 2 and a 5, because of course 2 times 5 don't make 10, and then having a factor of 10 gives you a 0 on the end. So, but you can't do that if you only have one prime factor. You require 2. So this is definitely true. You just can't end in a 0 if this. So that's true. Now this one here, if this, we cannot tell if n is prime. So what I need to do here is I need to find a time where it is prime and where it isn't. Because that way I could say I can't tell, because there are examples of both happening. So okay, the obvious thing to do would be to pick one prime factor and ends in a 1. And that isn't too hard to find. The number 11 has one prime factor, 11, and ends in a 1. So that obeys this formula. And that is prime. But then you could think of the number 10, which has two prime factors, so this is 2, and its last digit is a 0. And the reason I thought of this counterexample, of course, is because of this work that I had done 2 seconds earlier. And therefore I can find an example where this is prime and where it isn't, or an example n that is prime and isn't. So I can't tell, right? Because there are examples of both things happening. Now this last one, if you've got two prime factors, all last digits are possible. Now again, this is similar to the second case here. I need to go through all of the last digits and show that I can find numbers that have two prime factors. The thing is, this seems a little bit easier. Maybe people disagree. I thought this one seemed easier to show exhaustively than this one, so I chose to tackle this one because it seemed easier. N is 21 means I've already got an example of a number ending in 0 with two prime factors, right? 10, 2 and 5 are its primes, and it ends in 0. So this number here ends in a 1 and has two prime factors, that's 3 and 7. This ends in a 2, has two prime factors, 2 and 11. This ends in a 3, 3 and 11. As you can see, a nice little pattern going on there. 4, you can't use 4 and 11, of course, because 4 isn't prime, but you can use 14 because it's 2 and 7. You can use this. You could have used 55, of course, 5 and 11. But this works as well. Again, two prime factors. 26, 13 and 2. 7, I think I was thinking for a while about, and I'm trying to remember what example I did find. I can't. 77, of course. 7 times 11, yeah. 8, you can choose 38, 19 and 2. I think that one took me a couple of moments as well. And then 9, of course, you can just choose 39 because that's 3 and 13. I believe it is anyway. So that's cool. Two prime factors. So that's every single last digit with numbers that are just made of two prime factors. So this is definitely true. I can do that, which means this one must be the false one. Now, for the sake of completion, let's just show that. I know I said that I was avoiding trying to do this because I think it's difficult, but let's do it for the sake of completion. So I'm looking for just considering numbers that have one prime factor. There are some last digits that mean n must be prime. Now apparently this is false because all the other ones are true. So what I apparently can do is find any last digit with non-primes that do this. So for example, 81 is 3 to the power 4 and ends in a 1. So, and it's not prime because it's 3 to the power 4, so it has one prime factor, and so ending in a 1 means that it's not prime. And I just need to do this for every single last digit. Now notice I started at 1 because I can't start at 0 because none of these end in a 0, as stated here. 2, I can think of 32 because that's 2 to the power 5, not prime. 3 is 243, that's 3 to the power something, I don't really care what. Or is it 7 to the power something? Is it 7 to the power 3? I think it is. Cool. 4 is 64, 2 to the power 6, is it? 5 is 125. Could have just gone with 25 thinking about it, but anyway. 6, 256, 2 to the power something, don't care what. This is 3 to the power 3, 8 is 2 to the power 3, 9 is 3 squared, and that's all of my last digits running through. So there are no last digits that mean n must be prime. If this, because I found counterexamples to all of them, none of these are prime, but they all do this, so this is false here. Anyway, that's the entire paper, or at least the first section of the paper.